Hi, I'd like to do number 11 in section 3.2. And this would be a very nice guide for when you do your homework. Okay, here we go. So here's a differential equation that we're trying to solve. Okay, and the idea is that we have these three infinite series. One for y. If we differentiate y, we get y prime. If we differentiate y prime, we get y double prime. So what we'll do is we'll plug those into the differential equation, as you see in this line. Okay, and now we will manipulate the infinite series until we can get a nice recursive relationship amongst the coefficients. So the first thing we're doing here, let's see what's going on here. Well, I guess I'm multiplying the coefficients into the infinite series, the 5, the 2x, and the 10. The critical thing to notice here is that you see how this n minus 1 has changed to an n. In other words, when you multiply by x times x to the n minus 1, that increases the coefficient. Okay, the next line, let's see what happened here from this line to this line. Okay, notice here I changed this n. This is a bit of an odd thing to do, but I changed this n to a 2. Now the reason I can do that is because when n is equal to 0 in this term, we get 0, and when n is equal to 1 in this term, we get 0. So we don't need the first two terms there. That's all that happened in this line right here. I hope. Okay, yes. All right, and then the next term, this is a little odd, but this is the way I like to do it. In the next expression, I go back to n is equal to 0, but now what I do is I actually take what used to be n in this expression, and I actually increase it by 2, so that, again, nothing has really happened. If I start with n equals 0, I now put an n plus 2 in there for n, and I put an n plus 2 in for n in the second factor, and I get n plus 1 here. And I get, now notice the subscript of the coefficient c sub n has now changed to c sub n plus 2. And notice the exponent of x has changed from n minus 1 to n. And that's a critical part of this problem, as are all the calculations in this. So, okay, then moving on to the next line, what happens? I don't think anything happened. I noticed that when I was writing it for some reason. I just copied everything. But in the next line here, what I've done is I've realized that since I'm summing from n equals 0 in all of these three summation signs, essentially I can add all those terms together and just have one summation sign on the outside. So I'm summing n equals 0 to infinity of this entire, let's see, this entire term here times x to the n is equal to 0. And this is where we get our recursive relationship, because if the coefficient of x to the n on the left-hand side has to be equal to the coefficient of x to the n on the right-hand side, and on the right-hand side we just have the number 0, so where is it? All right, so 0, okay. So that means that we get the following recursive relationship, that this is the relationship, and this is what we will use to try to come up with a general formula for our coefficients c sub n. So what I do in the next term here is I write down that if I take this number times c sub n plus 2 is equal to this number times c sub n. Now, if you solve for c sub n plus 2, maybe I'll do that real quickly here, because that will come up again. Let me move this over here. Okay, so what I did, let me put this. Okay, because when you're doing these problems, you need to have, so this is minus c0. Okay, so let me solve this. So what I did is I said, okay, so we have that relationship. Well, that gives us a way of finding the coefficients. So this business right here, that you solve that equation for c sub n plus 2, you get this equation. You get c sub n plus 2 is always equal to 2 times n minus 5 divided by 5 times n plus 2 times n plus 1, and then we have to multiply that by c sub n. So you see, this equation allows us to find the c sub n plus 2 given c sub n. Okay, so that's what I'm going to do here, is try to get an understanding of what the coefficients are doing. So this first expression is just saying, well, let's see, if I know one of my constants, c0, then minus c0 is equal to c2. Now I do the same calculation here for c3, and notice I see that c3 is equal to a minus 4/5 times c1. Moving on to the next one. At this point, I'm just trying to look for a nice pattern. Okay. Then we see that c4 turns out to be 1/10 times c0. C5. C5 is 4 divided by 375 times c1. I just abbreviated. I did the calculation. It took me quite a bit of time, actually, unfortunately. But c6 is c0 over 750. And then a very interesting thing happens here in this example for c7. See, at c7, we have the appearance of the 0 in the numerator. So that means that c7 is 0. But now if you think about it, if c7 is 0, then c9 is 0, c11 is 0, and that's what I'm saying here, is that for every, that's what those three dots mean, c sub 2n plus 1 is equal to 0. Therefore, c sub 2n plus 1 is equal to 0 for every n greater than or equal to 4. So that's a good thing. So now we concentrate on the even c sub 8, c sub 10, and such, and so forth. And here's a good bit of advice. When you're trying to find a general formula for something, many times it is good to not simplify things. And that's what I'm trying to illustrate here. So notice I have c8, and going through this process of plugging in, using our recursive formula, and also taking a c6 and replacing it with something times c4, taking c4, replacing it with something times c2, taking c2, replacing it with something times c0. You then get to this situation where you're looking at this crazy expression right here. And my advice to you is to, when you get to this situation, you have to try to find something that is a function of, in this case, of n. And then the hope is that if you can, see, since we're finding c sub 2n here, we're hoping, where n is 4, we're hoping we can find a function of 4. Because if we can, that's nice, then there would be some positive probability that that could be the general term. And if we're lucky, it will be. And that's essentially how you want to think about these things. All right, so let's take a look here. Notice that after staring at this for quite some time, I noticed the following. Watch. I'm looking at 1, 2, 3. There are 4 2's in the first product, and that's where this first 2 to the 4th came from. Okay. Also in the top, there's these 1's, they don't do anything, but there's this -3 times -5. So I just wrote that as 3 times 5. Okay. Now let's look downstairs. There's, I'll circle, so there's 1, 2, 3, 4. Okay, so there's 5 5's. Okay, so 4 of them I'm writing as 5 to the 4th. But look what else we have here. There's an 8, 7, 6, one of those 5's, 4, 3, 2, 1. So that's this 8 factorial. Okay. So what I see is I see that c sub 8, so let me write this down, c sub 8 is equal to 3 times 5 times 2 to the 4th times 8 factorial times 5 to the 4th. So this gives me an idea that perhaps for n, this is where this comes from, for n greater than or equal to 4, maybe c sub 2n can be is equal to, well, 3 times 5, which is 15. Oh, okay, then we get this 2n minus 7 double factorial. Notice that we have, where's the double factorial business? It doesn't really come out here, does it? Well, what that means, okay, double factorial essentially means you use the sequence essentially to generate the terms of it. So for example, let me do an example here. Here, I'll just write one down here. Suppose I had, here, do an example. So when I write 2n plus 1 factorial, okay, that's going to be equal to, well, let's start with n equals 0 here, okay? So that's going to be, what is that? So n is equal to 0, that'd be, let's go with 1, then we get 3, 5, 7. See how it isn't, ooh, double factorial. That's the meaning of double factorial. So you use the sequence to generate the factorial. So notice it skips, go to all the odd ones. Okay. All right, so that's important in that notation. So let's take a look. Now, so we want to prove this. Okay. Now the way we prove this is by induction, of course. So for n equals 4, we just did the calculation, and it actually it actually corresponded to that. In fact, if we plug in n equals 4 right here, then we get 8 minus 1 double factorial. In fact, it's 15, so everything works out fine. All right, so then moving on, we need to prove this. So the way you prove something by induction is that you assume it's true in the n minus first case, and that's what I'm doing here. And now we are going to try to prove that it's true for the nth case, and that is we need to confirm our formula for c sub 2n. Now, we have by our recursive relationship that this equation holds. Okay. Now, then by our assumption, using our assumption, notice we can get to c sub n is this product. I'll move that over a little bit. It's this product, and you can confirm that in fact that's what you get. Now, if you simplify that, you get exactly what we have. Now, let's maybe go through that. Notice up here, so let's see how do we get this? Where does the 2 to the n come from? Well, okay, if you take a look at 2 to the n minus 1 times 2, that's 2 to the n. Similarly, 5 times 5 to the n minus 1, that's 5 to the n. Now take a look at this term here and this term here. Okay, so you've got this term right here is 2n minus 7. Okay, so and then up here, this term right here, this double factorial, would have ended with 2 times n minus 1 minus 7. So by throwing this one in, you in fact do get this right here, this 2n minus 7 double factorial. Okay. We have the 15. That's good. And down here, let's look at the denominator here. Notice if I take 2 times n minus 1 factorial, then if I multiply that, yes, times 2n minus 1 times 2n, this jacks it up to basically being 2n factorial. And so in fact we get our formula for the coefficients. Wrapping this all together, we now can write down an expression for our general solution, which I've done here. So our general solution is that we have going through all of our calculations, y sub x is c1 times this stuff plus c2 times this stuff plus, I'm sorry, c0 times this initial terms of our sequence that don't, work very well with our coefficients that we discovered, times c0 times this mess. Now what we have to do next is find the radius of convergence. So to do this, we calculate, as we learned in Calculus 3, I guess, the radius of convergence of this series to find out when this is a function is calculated by finding the calculating this limit. Okay. So to do that, we look at the ratio of the c sub 2n term divided by the c sub 2 times n plus 1 term, as we're looking at right here. Using some algebra, what you find out is that this here simplifies to a product. You can confirm this. That's just basically inverting and multiply, as we say, which then simplifies to this. Okay, you can confirm that. And then when you take the limit of such a thing, you get plus infinity because the, essentially the polynomial in n in the numerator is degree 2, and the polynomial in n in the denominator is degree 1, so you get positive infinity. So the upshot of all of this is that this solution right here to our differential equation, our series solution, converges for all x, and it represents the general solution to the differential equation as given up top here. Okay, so I hope this helps. This should help you do your homework, but it could take some time to do these problems. These are definitely very detail oriented. So thank you very much. Bye-bye.